Our next speaker, going to be a virtual presentation by Professor Buvat, who is based in France. She's the head of translational research in oncology, based in Ossay. She's also an editor in for the Journal of Nuclear Medicine. So, Prof, I don't know if you've already connected, but if you've already connected in French, I hope I'm saying it correctly. Montour sous Cern.
Can hear me well. So first, I'd like to thank the organizers for their kind invitation, and I apologize for not attending in person, but I'm trying to reduce my carbon footprint, actually. So today, I will give a brief overview of artificial intelligence in nuclear medicine. So these are my disclosures. Okay, as you know, AI is currently invading the medical imaging field through dedicated journals, conferences, books, challenges, and AI-based products that are offered by companies. And nuclear medicine is no exception to that trend, as can be seen from the number of scientific papers involving AI and nuclear medicine. So this number keeps increasing every year, with over 1,000 publications per year referenced in PubMed only. An AI algorithm can actually be used at each step involved in the management of a patient undergoing a nuclear medicine scan, as nicely summarized in that figure. So it can be used first to enhance image quality and accuracy. AI can assist in image analysis to accelerate and automate image interpretation. AI can help us make new discoveries from the images. And last, AI can facilitate the optimization of the research and clinical workflows. So I will now give you some examples for each of these 4 applications. So let's start with the use of AI to enhance image quality and accuracy. A well-known example is that AI can be used to get high-quality images from low-count data, that is, using either shorter scan or lower dose scan. So for instance here, you can see that beta amyloid PET images of excellent quality can be obtained using only 1/100th of the usual injected dose. AI also makes it possible to produce quantitative images in challenging situations, such as the reconstruction of attenuation-corrected SPECT images when you do not have a CT embarked on your machine. So here you can see that the corrected images using an AI, no CT, are very close to the one you get using the conventional CT-based attenuation correction. And why are these applications so important? This is because beyond improving image quality, these developments can lead to new applications. For instance, low-dose imaging can enable PET scanning in pregnant women to see the functional activities in the fetus. Lower dose and shorter scans enable children scanning, possibly even without anesthesia in very small children. And quantitative imaging can be achieved using non-hybrid devices, sorry Thomas, for the departments that are not equipped with hybrid machines. So in addition to producing better images, AI will also assist the nuclear medicine physicians in image interpretation. Maybe the most obvious application is the automated lesion detection and automated lesion or organ delineation. For instance, here, you can see the automated detection of mediastinal metastases in a lung cancer patient from his PET-CT scans. The diagnosis can also be automated by the AI, where the AI is able to tell the nature of the abnormalities reflected by the tracer uptake. So for instance here, an AI can recognize that this is the uptake pattern of a patient with a mild cognitive impairment. And last is the automated calculation of relevant biomarkers, such as the total metabolically active tumor volume in PET. The manual delineation of all the tumor sites is extremely tedious if you want to manually estimate this TMTV. But it can now be fully automated using AI algorithm. And here you can see that the prognostic value of TMTV is very close when the segmentation is performed by an AI compared to when it is done by an expert. So AI can be used to automatically calculate these TMTV, which are prognostic factors here in a lymphoma patient. This task automation is also very important. First, it will allow to save a lot of time, which might be extremely useful given the staff shortage affecting many hospitals. Second, this will allow for expert interpretation of images anywhere where these AI-based interpretation tools are deployed, even in centers where there is not a huge expertise in certain pathology. Last, as underlined by this editorial published in Radiology, AI will make systematic and reproducible biomarker reporting a clinical reality. All those sophisticated biomarkers might be quite time-consuming to calculate, and if they can be easily estimated by an AI, they will be automatically reported. And this is crucial to better establish the clinical value of those biomarkers. And the same applies to dose calculation in molecular radiation therapy. We all know that performing these dose calculations is tedious and it is barely done, and the same dose is currently injected to any patient for a certain treatment. But the automated dose calculation can yield results which are quite close to what is obtained by experts, as shown in this paper. So such automation should be very useful to help demonstrate that customized molecular radiation therapy is indeed beneficial. Third, AI can also be used as a discovery tool. So here, the most common illustration is in the radiomic field, where many groups propose prognostic or predictive radiomic signatures. So a signature corresponds to a radiomic phenotype that is associated with what we want to predict. So the response to a treatment or the outcome of the patient, for instance. So here we want the AI to make a prediction that an expert can actually not make. So for instance, predicting the location of tumor recurrence after re-irradiation of head and neck cancer using baseline FTG PET scan. So also an expert cannot visually do it. An AI model involving a few radiomic features, so here it was up to 4, can predict which patients will develop a relapse in field, so within the re-irradiation field, and which one will recur outside the re-irradiation field. And this model, which has been published, has been recently validated on an external cohort. Another type of new discovery we can make with AI are those based on calculations that we could not do before. For instance, it is now possible to segment all organs from a whole body CT. And if we overlap that fully automated CT segmentation with the aligned pairs, we can automatically estimate the metabolism in each and every organ. Hence, we can explore the metabolic footprint in subjects as a function of their condition. So this opens very novel research perspectives. And we should not hesitate to rely on AI to make discoveries, because it has been shown that our brain is actually limited in its ability to process information. For instance, Miller's law states that the number of objects or pieces of information that an average person can hold in working memory is about 7. And more recently, it has been reported that a structure defined on 4 variables, together with the connections between these variables, is at the limit of the human processing capacity. On the other hand, a computer can store billions of numbers in its memory and can investigate the associations between all of them. So this is why it is reasonable to expect that AI will show us associations between image content and prognosis or outcome that we have not been able to identify so far. And last, AI can be used to optimize research and clinical workflow. The first obvious application is using AI for enhanced or accelerated scan reporting, for instance, using ChatGPT or alike. And second, AI can be leveraged for integrating data for patient management. So to illustrate how AI can assist us, with an MD colleague, we recently asked ChatGPT to write a PET-CT report, giving only a few clues about the image content, as you can see here. And here you can see what ChatGPT produced, which is actually a pretty comprehensive report. I let you read. And an MD could just quickly review such a report and edit it as needed. Similarly, in research, there are now a few tools, such as this one, that can be used to help you go through scientific articles. Of course, these tools are still very imperfect, but thanks to the competition between Google, Amazon, Facebook, and so on, they will improve very fast and they will become real personal assistant we can rely on. While all these developments are extremely encouraging and start becoming available in the clinics, many steps are still needed to achieve what I call trustworthy AI. So this is what we have at the moment. We have plenty of AI algorithms, architectures, and libraries to choose from. We have guidelines for developing new AI algorithms, and these are issued by learned societies. We have some public data sets, including the one provided through challenges. We have a lot of applications that can take advantage of AI, as I mentioned before, and we have plenty of proofs of concept and prototypes, including highly promising results, and that are produced by different labs or companies. Remember that there is a huge number of publications every year. So what else do we need? First, we need more well-curated data, because data are the oil of all these AI methods which rely on training. And garbage in, garbage out. So the cleaner the data that are used to train the algorithm, the better. We also need algorithms that need less data to be trained, or that can handle missing data, so that we can better leverage the database that we already have available. We also need more weakly supervised or self-supervised training methods, so as to reduce the annotation burden, which is needed when we use supervised learning. And last, we should try to take advantage of transfer and continual learning, and I will explain what continual learning is. So at the moment, you have to realize that many groups are developing independently AI models to solve many different problems for image enhancement, segmentation, prediction, and so on. But all these models are developed completely independently. Continual learning is the process of improving the AI models as we handle more and more tasks, but without forgetting what was initially learned for maybe a simpler task. And this forgetting is what is called catastrophic forgetting. So the idea is to build a learner that will take advantage of what it has already learned for another task. And so doing so, we would mimic much better what a real medical doctor does, that is improving on different tasks as he or she gains experience. We also need to strongly consolidate the validation of the algorithms. At the moment, most algorithms are evaluated technically. So proof of concept are published and technical evaluation is usually performed. But we need more clinical evaluation on broad enough data sets so as to fully characterize the impact of this algorithm on the clinical practice and on patient management. So we need to work more on clinical evaluation and post-deployment evaluation. And for that, we should share usable model. And luckily, many developers are actually sharing their models through GitHub. And there is also this interesting MONAI initiative from a consortium of universities that propose different AI models for medical imaging, and similar initiatives are performed by, for instance, the Medical University of Vienna or many other groups in our specialty. And the results of the evaluation of these models should absolutely be reported, be they good or poor, as this is the only way we can actually improve the models. Indeed, this is by identifying the cases for which a model does not work that we can improve and enhance that model by incorporating these challenging cases into the training set. So reporting positive and negative results in AI is crucial. And last, to facilitate the adoption of models in clinical routine, it is desirable to develop models that come with both an explanation and also a degree of confidence so that the user can decide how he wants to integrate the model results in his decision. For instance, here in cardiac imaging, the goal was to detect perfusion defect, and the AI produced a map displaying where the perfusion defects were found and with which probability. And it was found that readers using that AI outperformed the readers that did not have this AI assistant. So that's the blue curve against the green one. So in conclusion, AI is there to stay and will serve nuclear medicine in many respects. Preliminary results are extremely encouraging, but also call for cautious. Solutions do exist to overcome the current limitations of AI-based methods, and more than ever before, sharing data, models, and knowledge will be key for advancing nuclear medicine thanks to AI. With that, I'd like to thank you for your attention.
Prof, merci beaucoup for your magnifique presentation.